Good evening, one and all. At the onset, I welcome Dr. Sachin Kumar Jain, who obtained his master degree in electrical engineering from IIT Roorkee, PhD in electrical engineering from IIT Kanpur. Presently, he is working as an assistant professor in the Department of Electrical and Electronics Engineering at Indian Institute of Information Technology, Manufacturing and Design, Jabalpur. Before joining IIITDM Jabalpur, he worked with the India's largest power utility NTPC for more than 5 years, where he worked as a engineer project and senior engineer operations and maintenance. For his outstanding work, he received GM Special Award in 2005 for his contribution for breakdown handling. His PhD research work also awarded with the prestigious Poshoko Power System Award in the year 2013. He has experience of working with real-time digital simulators and hardware circuits. He has undergone various professional trainings during his academic career. He has authored more than 60 research papers and 2 book chapters, 2 IPRs. His Google H index is 11 with more than 700 citations. His research interests are power and control, power quality, real-time simulation, and OpenRT hardware platform. So with this brief intro, I would like to request Dr. Sachin Jain to please start the today's session.
Thank you very much, sir, for the introduction. Can you hear? Can you see my screen?
Yeah, quite visible, and your voice is also very clear.
Okay. So,
presentation mode. If it would be better if you will do in presentation.
Yeah, I think it's in presentation mode. Isn't it?
No.
Okay, let me just change it.
Now
is
it's
it
fine.
Now in?
Yeah, it's fine.
Okay. So, good evening to all of you. This talk today is divided into 2 sessions. The first session will be on introduction to signal processing, and the second session will be on applications of signal processing methods to power quality. So, as you may be knowing, that signal processing itself is a complete 1 semester course consisting of 40 lectures. So I will try to give you what is important to you in this application with respect to electrical engineering or with respect to applications in power system or power quality. And that's why the talk will consist of some fundamental concepts of signal processing after briefing you about the basic concepts of signal processing. Then we'll discuss about some basic signal processing operations, signal manipulation, filtering, convolution, transformers, which basically constitutes a total signal processing arena. Then we'll discuss about some signal processing applications, followed by conclusion. So this is the agenda for the first session that I will try to cover in around 45 minutes so that we can spend more time in the next session. It depends upon you how much basic concepts you have in signal processing. Accordingly, you can ask me to skip particular contents if you find it's too basic, because considering the input received from the organizers about the constituents of audience, they are from undergraduate to faculty level, means they are quite diverse. So I have tried to keep this first talk to be more fundamental, more basic, and the second talk more advanced, consisting of the recent trends and state of the art techniques about that. So we'll start with signal. We all know what is signal. Something that varies with some independent variable. That independent variable may be time, temperature, or pressure. Most commonly, it is a time with which we consider something as a signal. But if we see, signal needs to be characterized by some specific parameters that define it in a complete sense. For example, what is the amplitude of the signal? What is the shape of the signal, phase and frequency? Now, based on these characteristics, we can identify any signal. Okay. Now, my question to the audience is noise a signal? It will be better if we keep it an interactive session, and if you also participate in the discussion, so it will be better. And that way I will get some feedback about your understanding, so that accordingly I have to customize how much contents I have to cover. Otherwise, even this uh, session could be of more than 2 hours duration. Anyway, as we define, it is an unwanted signal interfering with the main signal. That's how we define a noise. So it is also a signal which is unwanted, but sometimes it could be very useful. For example, in any machinery, if we are getting any additional noise, that could be a signal of something wrong in the operation of that, or some possible mishappening or breakdown of that device. So that's why noise is also considered as a signal. Let us say voltage and current in electrical systems are signals. In acoustics, we may have our speech, that could be a signal, audio signal, biological signals. We may have a lot many signals, image processing, uh, medical field, so many places we find these signals. Uh, Almost it is omnipresence kind of thing, which is nowadays is applicable to almost all kind of industries, all kind of commercial and all applications. Now, how signal, data and informations they are related? Signal is basically some variable that carries individual some information from it, but that may be hidden in it, or that may not be incomplete, that may not be purely visible. So signals together constitutes data. Signal of longer duration when stored together could be data. Multiple signals together could be a data. And data in itself is not very useful. But when we process it, when we properly present it, then it gives us some information. And then information helps us in decision making through inference and proper logic base. For example, in electrical system, we may have voltage, current, or status signal of circuit breakers, isolators. So this constitutes our signal. These together provides us, they can be considered as a real-time power system data at any instant. And this real-time power system data, when seen together, comparing their instantaneous values together, then they constitutes some information that there is a short circuit fault, or there is no fault or something. So based on that, we may take a decision that yes, there is a need to trip the circuit breaker. So that's how the system goes on. Now, the question comes, what is signal processing? We discussed about signal, and we all know when we process the signal such that any of its characteristics gets changed, maybe its amplitude, shape, or phase or frequency, or we manipulate or combine some signals to extract more information, or we present it in a better way, or we refine it to remove unwanted noise, or maybe if we want to compress it, any kind of manipulation, that is termed as signal processing, right? Now the question comes, why do we need signal processing? We have signal, we can have interpretation from it. Why do we need signal processing? So basically, the original signal that we have obtained, that we have acquired from the physical device or physical system, that may be corrupted with noise, that may not be complete, that may not carry visible information, and that may be there may be intermittency in that data. So we need to transform it to a more meaningful, more effective, easy to store, easy to visualize, easy to interpretation format. And that's how where the signal processing plays its role. There are different types of signals. I think I can skip these basic fundamental concepts if you agree. But if you would like me to discuss this, then you please let me know. Different types of signal we know about: the continuous and discrete signals. The continuous signals are analog signals, basically, which are defined in continuous domain, whereas the discrete signals are defined only for discrete values of independent variable. I have given you two examples here. Another thing is that the mathematically it is expressed like this with continuous signal, and the discrete signal is defined for integer values of sampling in terms of different sample, different time instances, or different integer independent values. Analog and digital signals, although they are almost analogous to continuous and discrete signal, but this digital signal is basically specific because it has to be represented by a finite number of digits. A discrete signal could be analog in nature, but a digital signal is something which is defined using finite number of digits. Generally, we use conversion, analog to digital conversion, for representing. So it is in binary digital form. That's how we define the digital signals. Then we have deterministics or random signal. Deterministics means it is defined through mathematical expression. Random signals means there is no certainty. It is probabilities. It is defined in probabilistics way, and it could have any random values. So that's why it is more uncertain in nature. The even and odd signals. Why I am discussing about these types of signals? Because based on the type of signal that we have to process, we have to choose the available signal processing technique. And there are some common phenomenon that we can apply their mathematical representation while we are modeling them, while we are simulating them. That's why we should always have the knowledge about the types of signals. So it could be a periodic or non-periodic signal. Periodic means it repeats itself after some time, specific time period, whereas non-periodic or aperiodic signal, it is again not defined in particular format. So it is not easy to describe them using mathematical equations because they are not periodic. Now, in signal processing, when we talk about some fundamental concepts, then usually we hear about what is time domain and frequency domain. And I have observed that many of us, including I have observed as senior research scholars, they are sometimes confused. Although they work in time domain or frequency domain signals, but they are very confused about what is time domain or what is frequency domain. So time domains means my signal is with respect to time, means it is defined on time scale, whereas a frequency domain signal is defined on frequency scale with respect to frequency. Now, what is key idea and what is relation between these domains? It is something like we transform one currency, Indian currency, into US currency. So only the domain has changed. So there is some transformation rate that $1 is equivalent to 70 rupees. So that's how we can represent it in that domain, that currency. So similarly, it is available, it is possible here. A time domain signal means, for example, this signal, as we can see here, this is a time domain signal. So with respect to time, at times t is equal to 0, 1 second, 5 seconds, what is the value of the signal? That is in time domain. But in frequency domain, it tells what are the frequency contents of that signal. For example, for DC, its amplitude is 5. In other case, if we see, The time domain signal, it may have multiple frequencies, but when we represent it in frequency domain, it is characterized that it has got three frequency component: fundamental component, third harmonic component, and fifth harmonic component. And this is their amplitude. So they together, if we combine these three signals in time domain, they will look something like this. So it gives you the instantaneous value and it gives you the constituents, what type of signals are there. So both domain have their own importance, both domains have their own applications, and we should be careful when we have to use time domain, where we have to use frequency domain analysis or frequency domain representation of any signal. Generally, oscilloscope is a tool used for seeing the real world signals in time domain. For frequency domain, the most common representation is Fourier series or Fourier transform. It transforms any signal into the Fourier domain. Okay, so some more discussion about time and frequency domain. I think you can go through these slides if you have to study about it. Another important concept in signal processing is about sampling, because we usually work with digital signals, digital signal processing, and we need to sample a signal, but we don't know actually how to sample and what is the proper meaning of sampling, what is the sampling frequency. So that's why I would like to discuss that also. Most of the natural signals occurs in continuous and analog form, whereas the digital form is often required for easy processing. So the process of converting a continuous time signal into discrete time signal is known as sampling. For example, if this is a continuous signal, we sample it at pre-designated places some time after a time interval. So these points, they constitutes your sampling instances, and this is known as your discrete signal or a sample signal, and this is known as sampling instance, right? Now for sampling, the original signal is like this and your sample signal will look like this. So it is defined only for discrete instances where you have sampled the signal, right? Now, what is sampling rate? The rate or the frequency or the time interval after which we sample the signal, we pick the value of that signal, that is known as sampling rate. Actually, as we have seen in the previous slide, this signal is changing continuously. And in the time while we are sampling it, it might change. So the real physical process, how we sample it, is done through a sample and hold circuit. So while we are sampling, it is like a switch. We just close it and we store that value in a memory, in a flip-flop, so that value is kept on hold until some new value is acquired. So if this is your original signal, through sampling and hold, it will look something like this. Means we have sampled at this instant. If this is our sampling period, then the value will continue for this particular duration, and then again we are sampling at this instant, so this value will continue for this duration, this value will continue for this duration. So that's how we define this. So the T is termed as sampling period, after which we sample instant, and the reciprocal of it is defined as sampling rate. Now, as you can notice here, this is your original signal and this is your sampled signal, and they are not alike. Means in fact, in this particular example, it appears that there is a very huge error and it is not representing the original signal. So that's true that it is not original representation of that, but in digital form it is represented like this, and that's what lead to a quantization error. So what is quantization? When we translate a continuous signal, continuous signal will have infinite values, but when we are converting it using to digital domain, then digital values will be represented by some n bits. So the total values that it can take in the predefined range is 2 to the power n. Okay, so in that case, this, let us say this is your continuous signal like this. So some quantization error occurs because of this quantization process. This is known as quantization error. So let us say if this is your continuous signal, this is your quantized signal, means sampled or discrete signal, then the instantaneous difference between the original signal, analog signal and quantized signal is known as quantization error. And this is sometimes significant, and we need to take care of what will be quantization error, whether that is tolerable or not. Accordingly, we have to design our signal processing system. Nyquist sampling frequency is another concept related to sampling which is useful, which states that a band limited continuous time signal can be sampled and perfectly reconstructed from its samples if the waveform is sampled over twice as fast as its highest frequency component fh. I'll repeat. If your signal has highest frequency component fh, and if we want to reproduce that signal, or if we want to represent our signal in a proper way, then its sampling frequency should be at least twice of its frequency component. If your frequency is less than that, then it will result in some errors, some problems that we will discuss. That is known as aliasing. Okay, so Nyquist theorem is also known as sampling theorem. And what is Nyquist rate and Nyquist frequency? The Nyquist rate says that the threshold 2fh is known as Nyquist rate. Means it is defined as the attribute of the continuous time signal. That if it is your highest frequency, then twice of it should be your sampling frequency. That's how you define based on continuous signal. Okay. Whereas Nyquist frequency is the parameter or attribute of sampling equipment that you are using to sample it. How much will be the highest signal that it can provide? So that threshold is defined as fs by 2. Means that sampling equipment can faithfully represent the highest frequency fs by 2. I hope this is clear. If you have any doubt, you can please unmute yourself and you can ask me anytime in between. You can interrupt me and ask me if you have any questions. So as I told you, if your sampling frequency is not as per the requirement of Nyquist criterion, then an effect known as aliasing happens. For example, if this is my signal and I am sampling it here, then here, then here, then here, then your sampling sampled signal will appear something like this. So its actual frequency is this, but it is appearing as if this is its sampling frequency. So what is aliasing? When higher frequency components appear as a low frequency components because of inappropriate sampling is known as aliasing. And for that purpose, to avoid the aliasing effect, we use anti-aliasing filters as a common practice, right? Now we have already defined noise. This is typically used to describe a wide range of degradations in the signal. I have introduced in the previous slides for this noise. There I have told you that it is distortion, but it is not necessary. It could be any type of degradation. It may or may not be part of the original signal. In some cases, it may not be part of the original signal also. For example, this is your original signal. With some noise, it may be corrupted like this. So it appears like this, right? Now there are different types of noise, maybe additive noise, multiplicative noise, quantization noise, or quantization errors. These are basically useful in modeling. If you have the idea of noise, then you can properly model your system so that its mathematical representation will be reliable. Otherwise, when you are developing some simulation systems, if you have not modeled noise carefully, then your design system may not behave realistically in practical situations, right? Now, additive noise means something that gets added to the intended signal. Multiplicative noise means it gets multiplied or modulated with the signal, whereas quantization is because of conversion. There are many types of noise. I have restricted myself to just give you an introduction. I will discuss relatively detail about what is additive noise or what is white Gaussian noise or colorful noise very briefly, but not go into details. You should refer to any good signal processing textbooks if you are using, if you are modeling any system for your signal processing design. So additive noise means, for example, a white noise. White noise means, let me give you an example, that its power signal throughout its frequency range, it is uniform, means its power is uniform. But in case of pink signal, it has the its spectrum follows 1 by f ratio. Means, as I told you, the it has equal power over the range of frequencies. Okay, whatever frequencies it is noise it is happening, it is derived from the name white light. Okay, the pink noise, it has more low frequency weighted character than the high frequency character. In some other noise, for example Brownian noise or blue noise, it could be opposite. Okay, in Brownian noise it is again same low frequency weighted character, but it is 1 by f square rather than 1 by f. But in blue noise, it is opposite. It means the high frequency weighted character has more noise as compared to low frequency components, right? Now, what is Gaussian noise? When your noise follows a probability density function or distribution, which is like a Gaussian distribution or normal distribution, that is your Gaussian noise. For example, additive white Gaussian noise is very commonly used in modeling of measurement noise, and you might have seen in MATLAB AWGN is the command for that, means add white Gaussian noise, AWGN, that is used to noise. It is always defined in decibels. Okay, so what is the signal to noise ratio? This is how we quantify how corrupted is your signal with the noise. So with respect to original signal and noise signal, what is their ratio? If ratio is very good, that means in decibel it should be around, means it should be very high value. But if that ratio is small, then your signal is said to be not it is said to be corrupted with high amount of noise. In decibels, 20 dB noise is considered higher than 40 dB noise. 60 dB noise means smaller than this noise. So this is how in decibels the noise is this added white Gaussian noise using SNR is defined. Now, something related to real-time processing. Sometimes we use these words in our literature, in our publications, that this is a real-time system. But what is the meaning of real-time processing? I would like to focus on that. Real-time means, for example, if you are simulating your system on MATLAB, your 1 hour simulation may be completed in 1 minute if you are doing it for very simple system. For example, I am plotting a sine wave and I am amplifying it twice of times for 10 minutes, 1 hour duration. That simulation will be completed in 1 minute. On the other hand, if I am simulating a complex power system, then sometimes simulation of 1 second may take 1 complete day to simulate that. So this is known as not unreal time processing. Real-time processing means not less than the actual time, not more than the actual time. The processing time should match with your real-time clock. That's what is real-time simulation. Okay. Similarly, we have real-time processing. So it means if we are sampling this instant, okay, or we are sampling the signal during our system, and before we get the next signal, if we are able to complete our complete processing, then we can operate that system in a real time. So if your processing time is smaller than your sampling time, or your waiting time is more than 0, it is not negative, it means your system can operate in real time. So that we need to define, or that we need to take care of while we are designing the system. Whether our system is intended for real-time application, then we have to increase our computational resources so that the processing can be completed in the stipulated time, or we have to increase the sampling time or reduce the sampling frequency so that we can operate that system in real-time mode, right? I hope this is clear. So we have completed a discussion about fundamental concepts. So any queries up to this point by anyone? Any questions, please? No?
Even if you have any question, please you can ask regarding the first session.
Okay. So we'll continue if you don't have any queries. There are now many signal processing operations that we perform. For example, do you know any basic fundamental signal processing technique as an electrical engineer? I assume that most of you are electrical professionals. So, do you know any signal processing technique that you are aware of?
Fourier
Finding out,
transform.
yes,
Fourier transform.
okay. Okay, I'm talking about most fundamental. Generally, we use RMS, root mean square value. We might not know, but it is a signal processing operation because it is your signal. We are finding out the root mean value of this. So we need to perform some signal processing task. Then only we can get its value. The instantaneous measurement will be of these values. But we collect some samples and then we find out what is its squared average. That basically constitutes our root mean square value. So these kind of operations, these are, we'll discuss about some operations. First one is scaling. Scaling means we are multiplying a signal by some constant. So maybe your constant could be more than one or smaller than one. So accordingly, your signal may be scaled on x-axis. Now you can have time scaling or you can have amplitude scaling. Time here means your independent variable scaling means scaling of x-axis or scaling of y-axis, right? Both are possible. The y-axis scaling generally we term as amplitude scaling, and x-axis scaling is termed as time scaling because in most of the cases, time is your independent variable. It is represented like this time scaling. So we multiply the time by alpha, right? Now in amplitude scaling, we multiply it by amplitude. So amplitude gets multiplied by 2 here. Okay, so it is represented by same way. Instead of in this expression, it is alpha xt. Instead of alpha appearing here, it appears here, right? This is the effect of visualized form of scaling. If this is your scaling, nominal means original signal. If you see its time scaled version with x by 2, then you see here, you notice the scales here, that this scale has changed, means its value, which was only 2 or maximum 4, it has exceeded up to this. Now it appears like amplitude scaling because it is twice of this value. In time scale, it has elongated. It has elongated by twice. Okay. In minus 2 axis, it has compressed basically on time scale. Okay. This is what is your scaling. Amplitude scaling, time scaling, or in wavelets we call it dilation or contraction of the wavelet. So it is something like that phenomenon that we use in wavelet. Another could be shifting, where we shift the signal. For example, this is your amplitude shifting. You can have time shifting. This is the example of amplitude shifting, where amplitude has been shifted by 1. Okay, this is the example of amplitude shifting. From the 0, it has been shifted here plus 1.5 or plus 3. So that's how we have designated it. Reversal is possible, where we get the images, mirror images, maybe either along x-axis or y-axis. So this is basically reversal of the signals. All these operations are part of signal processing and very useful in your signal manipulation or getting the real-time values or some meaningful values from the signal. Now, filtering, one of the very important signal processing technique that is generally considered synonymous to signal processing. Most of us, those who are not well aware about signal processing, they consider that signal processing means filtering the circuit. Okay, but it is just part of a signal processing, one of the many signal processing operations. In the filtering, basically, what we do, as the name suggests, we filter out some unwanted component, or we separate two components which are of interest to us. So that's how we can define the filters in different categories in terms of their function. It could be low pass, high pass, band pass, or band stop filters, or it could be a all pass filter. All pass filter means a filter that passes all frequency, but it shifts the phase. Its phase of the output is modified. Then it is known as all pass filter. These filters have been defined here, means they have been described. Low pass means this is known as your pass band, means your frequency range which will be through the filter, and this is the frequency components which will be stopped, because low frequencies are carried through this low pass filter. This is known as low pass. In band pass, only the limited frequency range is passed. In band reject, limited frequencies are stopped, but entire signal, other signal is passed. In high pass, high frequencies are passed, but low frequencies are attenuated. Okay, we should be aware about some common terms about the filters. For example, attenuation. What is attenuate? It means to decrease the amplitude of an electronic signal with little or no distortion. Cutoff frequency means the frequency beyond which the filter will not pass a signal. Transition band means the transition from pass band to stop band. Okay, the roll off means how steep is your transition band. That is basically roll off. So for example, in this signal, this constitutes your, this is basically attenuation. This signal is full here, is attenuated to zero value. This frequency signals are attenuated by this. This is basically your cutoff frequency, and this is known as your transition band, where your signal is under transition, and this is your roll off. If your roll off is small, then this will be your transition band. This sharp transition means your roll off. So roll off decides basically your transition period, right? Now, filters can be classified in many ways, such as it could be a non-linear or linear filters, time variant or time invariant filters. But the most common classifications that we encounter is analog versus digital filters. The analog filters could be passive or active filters. For example, the RC circuits that we use, or LC filters that we use in our power electronic circuits for passing some DC components or for blocking some high frequency components. They are basically examples of active passive analog filters. In some other analog systems, we use amplifiers or op-amps for filtering out some frequency components. They are basically known as active analog filters. Most of the high processing applications, they use digital filters now, which are very popular now. The two most common forms of digital filters are infinite impulse response filter. We commonly call it IIR or FIR filter with finite impulse response. Now, what is the meaning of infinite impulse response or finite impulse response, or what is their architecture? As I told you, the time is very short for covering this entire things. I'm trying to cover as much as possible, but I'm just giving you a glimpse of what is FIR or IR filters. Basically, they are represented by some filter coefficient, for example, H. And if you have input signal X, then basically there is some operation between these two that happens, and that produces the filtered output. Okay. So in case of finite impulse response, basically, if you give some impulse, okay, just impulse to this input signal, then the output response will decay down like this. Okay, so that is known as finite impulse response. But in case of In infinite impulse response, your response will be like this for, or it will be like this for IIR filter. Both have their own pros and cons. As we know, every system which is developed for overcoming the drawbacks of one system, but it has some other drawbacks. It introduces some other drawbacks. So same is true here also. The FIR filter is extremely stable, but when it comes to the implementation, then IIR is considered to be a much better, because it requires few mathematical operations per input data sample. So it is easy to implement, or it is, you can say, very cost effective. So there are pros and cons that we have to decide while deciding whether we have to use FIR or IR filters. Another very common mathematical concept that is part of signal processing is convolution. Okay, it is basically an operation that represents, it will be better instead of mathematical term if I would like to explain you through a visual explanation that what is convolution. We have two functions which have to be convolved, for example fx and gx. So this function gx, it is moved through that signal, and their multiplication or their integral, how much they are overlapping, that constitutes your convolution. So this blue color function, that basically is the convolution of f and g, and it is represented through f star g, as I told you, f star g in this form. Okay, and it is mathematically defined as integral of two functions. While window is sliding, this tau, it is sliding from minus infinite to infinite. In that zone, it is sliding like this. So this is how we define. It is very popular in digital filters design. In fact, the IIR and FIR filter that we have discussed. Now, I would like to touch upon about transforms. You may be knowing about the fundamentals of the transforms, because in our network courses, network analysis, control systems, you might have studied about the Fourier transform, Laplace, wavelet, and jet transforms. I would like to discuss something apart from the basic known things. Means we know what is Laplace transform. It translates continuous time signal ft to S domain. Now, what is S domain? S domain means it is your basically, S means sigma plus j omega, where sigma denotes your exponential term. If you express sine waveform in terms of this, I don't remember that explanation, Euler's form. Okay, Euler's form, e to the power j omega, like this, then this constitutes your how much decay it is having exponential term, and this constitutes your continuous or sustained oscillation part. So this is basically frequency domain part. Okay, so Laplace is more general form of Fourier transform, because Fourier transform translates ft into only j omega form, and it considers this also. I have a visual way to explain that. So it analyzes signal in terms of sinusoids and exponentials. Okay, now how it helps? It helps in following ways. It finds solution to differential equations using algebra, a very popular use that we have seen. No need to learn about how to solve differential equations, the traditional ways that we have studied in our basic mathematics course. We have basic part and this part, so that's how we can solve differential equations. And it is very useful for multiple process system, which is difficult to solve using normal differential equation solver without this Laplace domain. So this is just illustration of how we have to do it in time domain without using traditional method. We simply solve this using differential equations, but through Laplace transform, we first convert into Laplace transform, solve it as a normal algebraic equation, and take inverse Laplace transform, we get the same solution. So this is for simplification purpose, we use any transform. It is defined like this, we know. I would like to give you the visualization of what basically is Laplace. If this is your time domain signal, right? So how many frequency it has, that will give you Fourier transform. And for difference exponential term, analyzing that signal with that, what will be its representation? That is basically known as your Laplace transform. So it has your Fourier transform along with exponential term. So for different values of for sigma, means for different values of exponential slope, what is your Fourier transform? So that's what is the representation of Laplace transform. So I hope this figure will give you some insight about Laplace transform. Now, what is Fourier transform? I have already introduced you from while explaining what is time domain and frequency domain, because Fourier transform translates a signal from continuous time signal ft into frequency domain signal, like fj omega. Means if any signal, it has multiple frequencies, so in time domain we get its instantaneous value, but at this point how many frequencies are present, that can be obtained by transforming that signal into using Fourier transform into frequency domain. So Fourier transform is a means, or it is a tool to convert a time domain signal into frequency domain signal, and this is very useful concept in signal processing and many other branches of engineering and physics also. I will not touch upon the mathematics part because I hope that you all know about it. So I will just discuss again about the visualized form of Fourier transform. Just like a complex light wave, a white light signal, when it is passed through a prism, it translates into high frequency and low frequency components, that we get a spectrum from the prism, or rainbow side, 7 colors out of it. Because it is consisting of all these 7 colors. Same is true when a signal has multiple frequency components. When we use the Fourier transform, it provides us individual constituents of in terms of different frequency. For example, if it is a complex sound wave, it will give you what is treble, what is mid range, and what is bass of that frequency signal, right? Of that speech or sound wave signal. So now you might have heard about what is Fourier series, Fourier transform, discrete Fourier transform. So often we get confused about it. So again, I am trying to use one visual representation of what is Fourier series and what is Fourier transform, what is DFT and what is DTFT. They all transform a signal from time domain to frequency domain, but it depends upon the type of time domain signal and type of frequency domain requirement, that whether you have to use Fourier series, Fourier transform, DFT or DTFT. Fourier series transforms a continuous time domain signal that is periodic in nature to a frequency domain signal which is discrete in nature. Okay, so that is basically Fourier series. This signal is continuous in nature and periodic, and we are getting a periodic discrete signal. So that's what we are using Fourier series, right? In Fourier transform, basically for a periodic continuous signal, we get a continuous frequency domain representation, right? In case of discrete Fourier transform, we have a discrete signal which is periodic, and we get a discrete Fourier transform which is also periodic. But in case of discrete time Fourier transform, our input signal is discrete in nature, or time domain signal is discrete in nature, but we need a frequency domain that is continuous in nature. So we use discrete time Fourier transform. So that's what I have represented here. Fourier series, when you have a continuous and periodic in time, or you have discrete periodic in nature, so then we use Fourier series. Fourier transform, it could be aperiodic or periodic but continuous in nature. So these are the mathematical expressions for using the Fourier series, Fourier transform, discrete Fourier transform, or DTFT. One more thing, can anyone answer what is difference between DFT and FFT? What is difference between DFT and FFT? Yes, Any answers? I'll be happy if you answer. Even if you don't know, just let me know, so that at least I get that whatever I am telling you, the information is something new and it is not repetition to you. So if you know, please let me know. If you don't know, still please let me know that you don't know what is exact difference between FFT, fast Fourier transform, and discrete Fourier transform, DFT. Any idea? Can you hear me?
Sir, one is continuous and another one is discontinuous.
Okay, any other answers? No? While I'm taking break to drink water, you have a time to think and please try to answer if you can. A fast Fourier transform is a means to compute discrete Fourier transform. It is a method, it is a mechanism. Fourier transform, theoretically it is there, but if you have to implement it in algorithm, if you have to implement it in hardware format, then fast Fourier transform is used to implement DFT. It is not like that one is for continuous, it is Fourier transform. Fast Fourier transform is a mechanism. For example, we use radix 2, radix 4 concepts. It is a algorithm or mechanism to compute discrete Fourier transform in a very rapid manner. Okay, and it is well suited for digital implementations. So that's what is the difference between DFT and FFT. So be careful when you are using these terms as a synonymously in your literature. They are not same. One is a technique or a tool, whereas another is a concept. For example, DFT, which translates from discrete time domain signal into discrete Fourier, frequency domain signal, right? Okay. Z transform is another thing. Now, what is Z transform? Z transform is nothing but your Laplace transform in discrete domain. Okay. So in this thing, basically when we replace the Z is equal to e to the power st, then we get the S complex domain. If we translate it by j omega, then we can get the frequency domain representation of the same signals. So I'm not touching about the Z transform again, because we have to finish about the, okay, what is wavelet transform and where is it useful? The wavelet transform is useful for you can say time frequency resolution, because in Fourier transform, in time domain signal you have time, no information about frequency. In Fourier transform you have information about frequency, but information about time is lost. In wavelet transform we get both information together about time and about frequency. So it uses a multi-resolution technique where you get both time and frequency resolutions. I'm not discussing these things in detail, but I'm trying to introduce you about these concepts, that where you can apply these concepts in your real life processes, or in your research, or in your techniques. So what happens in Fourier transform? As I have told you in the Fourier transform, if you have some signal like this, okay, then we can represent that it consists of one frequency like this, it consists of another frequency, high frequency like this, and it consists of another very high frequency component like this. When we add these three signals, then we will get this signal. Okay, so this is time domain representation, and this is frequency domain representation, which is represented by three frequency components. It uses sine waveform, Fourier transform. But in wavelet transform, instead of sine waveform, we use wavelets, which are localized in time. And that's how we get the time information about this. Okay. Now, what are wavelets? They have basically, the wavelets are defined like this: for very short duration. For remaining duration, they are 0. But for short duration, they have some amplitude and some variation. The another key feature of wavelet transform is the wavelets are available in large different variations. So these large variety of wavelets can be uh, specifically chosen for a specific application, so its operation or transform is much better. For example, this is known as Haar wavelet, this is known as Quafflet wavelet, this is known as Devich's wavelet. So they are like this dB4, dB16, there are different wavelets. So these are basically a wave-like oscillation that is localized in time. These are literally little waves, small oscillating waveforms that begin from zero, swell to a maximum, and then quickly decay to zero again. They have two basic properties, like we can scale it and we can locate it. So dilation and location, it is used in wavelet transform. I hope I have some. This is the visual representation. This is one wavelet, then it is scaled, and this is the time scale I am using, and this is dilated form. Okay, scaled and dilated, and their correlation is then obtained to get either continuous or discrete wavelet transform. You can have continuous wavelet transform just like your Fourier transform, or you can have DWT just like your discrete DFT. Okay, so this is the representation that you can have. You can go through the signal processing books for getting the details about this. So a quick comparison, this is your time series signal. So in Fourier transform, you have no time information, only frequency information. Here you have no frequency information, only time information. In short time Fourier transform or Fourier transform, you can have frequency resolution also and time resolution also, but you have equally spaced. So time and frequency resolutions are basically same. But in case of wavelet transform, you have multi-resolution capability. At high frequencies, you have low time resolution. At low frequency, you have better time resolution. So that's better frequency resolution at times. So that's what is the quick comparison of different Fourier transforms. You can choose anyone that you need. This is another representation or visual comparison of transforms. Like Fourier transform will give you something like this for a square wave like this, whereas its Laplace transform will be something like this. So if you see, if you ignore this real axis part, that is sigma part, then imaginary axis part is same as your Fourier transform like this. But this has this additional information in Laplace domain or S domain, right? If you have it's what I call wavelet transform, then wavelet transform will give you in this real axis, you will have time axis here. I could not get its representation, but it will have time axis. It will say that you have zero frequency component here. Here you will have high frequency changes here. Okay, then again low frequency changes here. So it will give you zero, something like this, and in this time you have these frequency components like this. So depending upon you are using DWT or CWT, it is represented in spectrogram, color coded matches. Some other useful signal processing operations are composition, for example, addition, multiplication, modulation, multiplexing, demultiplexing, denoising, decomposition. We have already discussed about these transforms, classification, estimation. These are different other processing operations that you can go through if you need it for your particular application. About applications, we know that signal processing available everywhere, whether in space, medical, commercial, telephone, military, industrial, scientific, everywhere you will find their applications. If you see in terms of space applications, this is we use radar, sonar in communication techniques. If we talk about image processing, so many we know about Adobe Photoshop. You can do anything using Photoshop. You can combine two pictures. You can create so many good things that we know about using Photoshop. So this is an example of image signal processing. In medical, we know about MRI, CT scan, wearable devices nowadays we are having, which can capture ECG signals. your pulses, everything. So this tomography, all these are examples of signal processing. Suppose this is your original EEG signal that we have obtained. Through signal processing, we can reconstruct it for a better representation, so it can give you better, basically, interpretation can be done in a good way. Now, in terms of power engineering, we'll discuss in the next session about the applications of signal processing power. In smart grid era, we need to process different signals in grid. So we cannot think of smart grid without signal processing, without data handling, without, you can say, information technology. The idea of a smart grid cannot be even imagined. And in fact, the idea of a smart grid was there since quite old time, but because it was not implementable, so it was not given a thought. But once we have these fast processors available with us in terms of computing devices, then this smart grid is now turning into reality by using those advancements in the signal processing. So we'll discuss about the applications of signal processing in power in the next session. So let me conclude you. It is a very crucial for industrial applications, but nowadays it has become more important because of many diverse applications. You might have heard about the autopilot vehicles, many wearable devices for health monitoring. With the development in fast computing techniques, the dreams have come into reality. Means what we could have thought earlier, they are now reality just because of rapid growth in the semiconductor technology and computing systems. Although simulations and software applications are important and they play a significant role in design of signal processing systems, you as a developer must have proper understanding of real life physical signals and the hardware systems, how you are going to process it, how signal flows inside it. Then you will be able to create your optimal and correct system design. Most of the signals in our environment are analog in nature. Therefore, understanding optimal design of ADC and DC is equally important. They are also part of signal processing. Unfortunately, due to time limitations, it is not possible for me to discuss about analog to digital or digital to analog conversions. Finally, just to bind up about this session, what is analog and digital signal processing? DSP is easy to change applications, correct applications, update applications, because we can just change the code and your entire thing is changed. But for very fast applications, we have to still go with analog signals because they work with real in real life because they are fast. Whereas the ADCs need some finite time to convert analog signal into digital signals, and that's where is the limitations at present we have in using digital signal processing, and analog processing still find its role. So that's what is about my first session on introduction to signal processing. So thank you very much. And do you have any questions up to this point? Any questions, please?
I think we will ask at the last of the both the session. That would be better.
Okay, okay. So I shall I start the next session, sir?
You can.
Okay.
Yeah. Right. You can start.
Okay, thank you. So we'll discuss about now the applications of signal processing methods in power quality. Again, I have around 80 slides in this discussion because, you know, power quality itself is a very huge field, and power quality and signal processing, they cannot go alone. Means they are varied like, and they almost go in parallel, because power quality means voltage sags, swell, flicker or something, and that you cannot get the information. So the agenda for today's talk will be some overview of the power quality parameters, and then some specific signal processing techniques for power quality applications, some fundamental concepts about them, some specific applications in frequency deviation, harmonics estimation, Maxwell, and then some case studies on harmonic measurement. And finally, I think the today's talk will be incomplete if I do not discuss about the hardware systems. If you have to use it for your applications, how you can choose or how to decide or what are the crucial things about it. So finally, we'll conclude with some discussion on overview of this. So what is quality? In general, it is essential attribute or character in someone or some entity, physical entity. When it comes to power quality, it is essential attribute of power, a degree or grade of excellence or worth that an entity should have. For example, as a human being, what are my qualities? To what degree I have excellence? How I am fit to a purpose? That's what defines my quality. If I am a good teacher, so that's what is my purpose. If I am fit for that, then I am a good quality about teaching. So similarly, the power quality is defined as the quality of what? Power, voltage, or signal.
Sorry, sir, but screen is not visible, sir.
Okay. I'm sorry. Is it visible now?
No, not
No,
now.
sir.
My screen is not visible to you?
No, sir.
Yes, sir.
Sir.
Is it visible now?
Yes,
Yes,
sir.
sir. Now it's visible.
Okay. There was some error in sharing the screen, so I'm sorry for that. So this is the agenda for today. We discussed about quality. So what is power quality? Quality of power, voltage or current? How do we define power quality? Come on, now it's about electrical engineering and you should be able to answer it. This is not about signals or something that you may not be master of. So
Quality of both.
both means power or voltage or current.
Voltage quality, sir.
Okay.
Sir,
In
I think
general,
both, sir, voltage as well as current, sir.
okay.
We need to maintain both, sir.
Okay, it depends upon the context in which you are talking about, but in general, when it comes to quality of supply, power supply, then we talk about voltage signal because this is what an utility provides to us. And the overall power quality, it includes both voltage and current. And the term is given as power because it considers both voltage and current. Okay, but there is no as such quality of power. It is about voltage and current signals. Okay. Now, why to worry about quality of power? Is it just a research propaganda? Because we have seen so many issues like this. It's not like that. There are many technical issues related to power quality, device maloperations, increased losses, device failures, visual disturbances. That's what we can really see. We can observe it, and there are very well-defined reasoning for that. There are many economic issues also. Production process disturbances, loss of productions. In fact, I have collected some data from different newspapers or magazines that how it is impacting in terms of economy. The poor power quality in US causes about 13.3 billion in a damage per year. This is IEEE Spectrum magazine report of June 1993. In some factories following a voltage sag, this is again I am talking about EPRI General 1993, that $50,000 per incident. Per incident, I'm not talking total yearly. Poor power quality is estimated to cost European economy up to $150 billion annually. This is again power quality initiative, and USC's losses ranging from this. So what I would like to say is it is crucial. So it is crucial now, or it was crucial earlier also. Earlier, the devices were mostly, they were intolerant loads were there, but today loads cannot tolerate. They are mostly power electronic devices or digital or electronic devices. They are very prone to any disturbances. But earlier, suppose we have an induction machine, if there is any voltage dip or something, or there any harmonic, just losses will increase, but it can tolerate, but not the same today. In deregulated energy market scenario, when there is a throat cut competition, or there is some something to worry about the existence of my survival of my as a utility, my whether I will be able to supply or not. So I'm sorry, please. Okay, okay. I'm sorry. So we have increased power pollution due to power electronic based nonlinear loads. So in both way means the power quality has become crucial. Earlier our loads were not sensitive, and the problem of power quality was not that much there. But today the loads are more sensitive, or systems are more sensitive, and we have more devices which are polluting our power system. So in both way it is now very crucial decision. So let us discuss about what is power quality and some terms about it before we enter into the signal processing techniques. The characteristics of power supply. Am I going very fast? आपको समझ में तो आ रहा है कि नहीं आ रहा है?
Yes, sir, we are understanding.
Yes, sir. Yes, sir.
Because there is so much to share with you, so I am trying to complete the things with you. But you should get what small or more you learn, you should be able to grasp it. So that's what I'm trying. So power quality is defined as the characteristics of power supply that enable the equipment to work properly. Okay. There are different parameters that we need to monitor. For example, its frequency, whether there is voltage balanced or unbalanced, there is any sag or swell or interruption in the power supply. For example, how they are defined, that you can go through different standards, that there is a specific definition that when we consider there is a voltage sag or swell, okay, or there is a voltage interruption. And this IEEE standard defines when any sag or swell is defined. It is defined as instantaneous, momentarily, or long duration variations. And these are typical duration and typical magnitude. So from this you can get the information, so I'm not discussing about it. Other parameters are voltage flicker, supply harmonic distortions, for example notching, noise, or harmonics. They also constitutes your power quality concern. Now we'll discuss some of these. Do you know about these power quality disturbances? So I'll come directly to the signal processing methods, or you would like me to discuss about their basic fundamental concepts? Yes? Do you know what is flickering?
Continuous change in the magnitude between 0.9 to 1.1.
Okay. And how it is different from voltage swell or voltage swag? Because in that also the voltage magnitude changes. So
In sag or soil, either sag means either it will be a particular level of 0.9, 0.1 to 0.9,
yes.
or 1.1 varying continuous from 0.9 to 1.1.
Okay, very good. Very good. So all are waking up now. Means you are still awake. I'm really happy to know that. So it caused disturbance to human visual perception. So it is basically related to frequent changes. It is not about one-time event that your load or voltage has dipped or it has swelled. Okay, it is about change in brightness of a lamp. This is how we perceive it, and it is defined or it is modeled as some amplitude modulation of the signal. So flickering is something like this, as you rightly pointed out, and it is related to perception of human eyes. And that's why, because we can, there is a definite frequency that our human eye tolerate, means it can perceive. So that is around 8.8 hertz is the boundary for that. So if your flickering or if your fluctuations are faster than that, maybe 50 hertz, 45 hertz or 40 hertz, then we not consider it as a flicker. Okay. The harmonic distortions, we all know that if there are disturbances, if your waveform is not purely sinusoidal like this, which is supposed to be, then using we can transform or we can represent it in terms of some higher order frequency components. If it is a periodic in nature, these higher order frequency components are defined as the harmonics. Now, because their frequency is very high, they lead to the higher losses and electromagnetic interferences or many other issues, skin effects or others. So that's why we need to take care of these issues. Then impulsive transients could be there. Some oscillatory transients like this should be there. All these are basically the power quality parameters like waves, swells, flicker, transients, frequency variation, unbalance, harmonics. So these are different power quality problems that we encounter. Okay. Now, why signal processing for power quality? Because detection is key. This is what is the title of one of the article in IEEE Industry Application Magazine in 2007 July-August issue. Now, why? What is the meaning of this detection is key? To be able to respond and react to any undesirable situation or to act, we must know about it. When we know it, we can take corrective action. If we are not aware about it, then we cannot. So it means we need proper monitoring. And that monitoring should be timely, it should be accurate, and it should be reliable. And that's why we may call it measurement, or you term it monitoring or sensing or detection. That becomes crucial in power quality disturbances. And because the signals that we have in electrical systems, because they work with sinusoidal quantities, they are sampled for instantaneous values of the sinusoidal waveforms. And that instantaneous value may not be of any useful means. For example, if your voltage, if you measure it at any instant, let us say this value is 300 volts. Now this 300 volts has no meaning because that instantaneous value you cannot use. So we need to properly process it to get its meaningful value. As I told you, for example, if you translate it into RMS value, so it gives you some information that RMS value is changing like this. So there is a dip here. Okay. With instantaneous, either you can monitor peak, but still you need to monitor it. So this is why we need signal processing. The process of power quality monitoring involves analysis and extraction of relevant features from sampled waveforms, which is possible only after processing of these signals. As I told you, that what is flickering or what is sag, when your voltage dips like this. So this is your RMS value, this is your instantaneous value. So in either way, you need to monitor that the amplitude has reduced and it has been there for some duration. Then only it will be termed as sag or swell. If there is a momentarily dip, and it is less than 1 cycle, then it will not be considered. It is just instantaneous and it is of no significance. Okay, so that's why we need to properly monitor it. For that, we need to extract the information, useful information from that signal. And digital signal processing concerns the extraction of features and information from the measured signal. So that's what is the basic idea, and that's why we need signal processing for power quality. Now, signal processing extracts and enhances the information that is hidden or not directly perceivable. Okay, and the process of power quality monitoring involves steps. For example, characterizing a variation. Suppose we have some variation, then to characterize it, then distinguishing between variation and event. Event means sag, swell, or tripping or switching. So just to distinguish between these things, we need some classification techniques or some triggering mechanism. Then characterizing each event through a number of parameters once the event is detected, to distinguish whether it is flickering or it is some other frequency variation or something, to classify each event according to its underlying causes from the extracted features. That's why signal processing is required. Now, as an electrical engineer, what is there for us? We have challenges and opportunities in the field of signal processing applications in the power quality. So before that, we'll discuss about some applicable standards we should know. We have many IEC standards, for example, 61004 series, where this 47 is for dedicated for harmonics, 15 is dedicated for flicker, and 30 is dedicated for general power quality measurements. For example, sag, swell, and other issues. Although power quality is general, but because flicker and harmonics are specific fields, so they have their dedicated standards 47 and 415. Okay. IEEE also has standard IEEE 519 for harmonics and IEEE 1159 for power quality, which includes your flicker and also. We should be aware about these standards while we are working on signal processing, or if we are working on power quality problems. So we should know about these standards which I have mentioned. Now, what are the attributes to measure in power quality? Maybe their amplitudes, maybe frequency, phase angle, source, notch, and apart from this, at what time this amplitude or frequency variation has occurred, what is the rate of rise of amplitude, if at all it is changing, what is the duration of the event, rate of occurrence, energy potential. For example, you might have heard about the PMU, and in today's scenario, we talk about rate of change of frequency, ROCUF. It is very important concept. So it is a frequency and its rate of change of frequency and time of event. All these things are there in phasor measurement unit because it records time also, it records rate of change of frequency also, and frequency also. These are different measures that we need in power quality also. This is a general block diagram for measurement scheme for any power quality problems. So you have measurement, sensing of some signal, maybe voltage or current. So you may have CT or PT here. Then you have data acquisition system that may involve your anti-aliasing filter, analog to digital conversion, sample and hold circuits. Then you have some data pre-processing. Suppose you have acquired your data, there are noises, there are missing data, there is some time skew or something. So you need to process it and then arrange it in a proper format. Then we use some signal processing tools, maybe some event classification, some harmonic estimation or flicker detection. Then once we know that, then we can send this event to data storage or reporting or for alarming or for tripping functions in our in our systems. So this is a basic block diagram. Now, how to have event classification, how to have harmonic estimation and flicker, everything is not possible to discuss here. We have discussed a little bit about the concepts about this in the previous session. Today, I will have brief overview about these things and I will focus some of the applications on harmonic estimation, right? So before we discuss that, there is some measurement philosophy that is used in signal processing for power quality disturbances. For example, RTC synchronized measurements, that is very much required. Aggregation, instantaneous values, for example, if you have RMS values also, they are uh, they are of no significance. So we aggregate generally maybe for 10 cycles or maybe for 180 or 150 cycles means 3 seconds. 10 cycles means 200 milliseconds or something, or for that durations, maybe for 10 minutes or maybe for 2 hours. So according to the standards, this is defined in those standards that we have discussed, that how much you need to aggregate. And that aggregated information is used for decision making in different points. Now, when we talk about 10 or 12 cycle, it depends upon. For 50 Hz system, it is 10 cycles. For 60 Hz system, it is 120 cycles or 180 cycles, right? Another concept is known as the concept of flagging. Flagging means when there is any event, dip or swell or interruption, then we flag it. Flag means we raise a flag, or we raise a kind of indication, some signal that there has been some event. During a given time interval, when any value is flagged, the aggregated value which includes that value shall also be flagged. What does that mean? Suppose your signal is, let me come to this signal, right? Now, because there is no change in frequency, there are no harmonics, but because this amplitude has changed, so at this particular instant, it will consider, your signal processing algorithm will consider that there has been some harmonics in the because there is a change in frequency component. Okay, so it will consider it that, but actually it is a voltage sag and swell. So when this event is detected, so there will be a flag that you do not consider this signal for this duration for harmonic estimation, or even if it is estimated, that value will also be flagged that it is for that duration. So this is the concept of flagging that is used there, right? The flagging concept is applicable during measurement of power frequency, voltage magnitude, flicker, and these things. So these are some philosophies that that we should know, that how these concepts are used. Now we'll come directly to what are different signal processing methods. It could be defined in two broad categories: non-parametric methods or parametric methods. Non-parametric methods means the methods which are non-parameterized. Means not parameterized means they are not model based. So they are basically model based, and these are non-model based. Non-model based means they rely on some basis functions. For example, sinusoidal functions in Fourier transform, wavelets in wavelet transforms. We have many other non-parametric methods. For example, Hilbert-Huen transform, it is not mentioned here, HHT. Okay, so all these are non-parametric methods. They can be in frequency domain or they can be time frequency domain analysis. For example, short time frequency Fourier transform or wavelet transform, they have time frequency domain analysis. In parametric methods, the philosophy is altogether different. The philosophy is different means instead of decomposing a signal, we translate or we model a signal in terms of some amplitude, some parameters. For example, a signal can be modeled as, this is its instantaneous value. It can be modeled as consisting of a parameter A, cos of omega t. So this A is your parameter, which is amplitude, omega is your frequency, it may have phase shift, so that is your parameter. So you are representing this signal by a model. This is your model. So then you can have some stochastic models or sinusoidal models. For example, split music, they are based on your sinusoidal model, or you can have stochastic models like autoregressive moving average, ARMA, Prony models, they are basically all stochastic models. So I will briefly touch upon these methods, just their strengths and weaknesses, so that you can choose how to use, specifically in terms of harmonic analysis I am using. So I'm talking about DFT using FFT, okay? So it has low computational burden, simple and most reliable for stationary signal. But the shortcomings are it has poor resolution, difficult to detect interharmonics, essentially requires analysis window to be exactly integer multiple of fundamental period. What does that mean? If this is your signal, then your analysis window should comprise of integer number of cycles. If it consists of non-integer multiple of cycles, then its results will not be perfect. Okay, it will not give you proper frequency domain representation. And the frequency deviation leads to leakage and picket fence effect. For example, you have defined this window for 50 Hz signal. And if your frequency has changed to 50.9, 50.1 or 49.9, it means in one cycle, your window will overlap or it will underweight. So it is again non-integer cycles will be there. So it will again lead to leakage and picket fence effect. These are very prominent in Fourier transform. In wavelet transform, it provides frequency and time information simultaneously. It has multi-resolution capabilities and most stable for transient detection. Okay, it finds its applications in transient detection. That's why for power quality like voltage sag, swell transient, wavelet transform is more popular than Fourier transform. Whereas Fourier transform is popular in harmonics analysis, okay, rather than other power quality events. But it has very high computational burden as compared to Fourier transform. It provides harmonics in terms of frequency bands. So it is not very good for Fourier harmonic analysis, and interpretation requires expertise, means it is not direct results. You need some expertise for interpretation of the results of wavelet transform. This is the way of wavelet packet transform. It is based on wavelet transform, but specifically for Fourier harmonic analysis, you can use it for in different frequency bands. So it is realized using high pass and combination of high pass and low pass filters. So in that way, its synthesis is easy. So wavelet packet transform using multi-stage filtering. Then comes the Prony's method. Now this belongs to parametric method. It is able to identify damped components also. In wavelet or Fourier transform, it is not possible. So just like your Laplace transform, if you have your sinusoidal signal which is decaying in nature like this, the Prony method will be able to find out what is this decay rate. So it is able to identify damped components and damping factor also, and it is very high resolution without leakage effect. So even if you have frequency component like 50 Hz and 70 Hz or 71 Hz, it will be able to distinguish, but Fourier transform won't be able to distinguish this 71 Hz signal. So, but it has very high computational burden and it is highly sensitive to noise present in the signal. And if your model order selection is not appropriate, then it may lead to high inaccuracy. This is how it is processed. Some from one of the papers. I'm not going into details because of time limitations. Kalman filter, again very popular and very useful technique, which has very versatile applications. It is very one of the biggest advantage, which is not there in any of the earlier methods that I have discussed in Fourier transform or wavelet or Prony method, that it is recursive in nature. Recursive means the previous results which you have with you, they will be used, and just with next value, new value, you just discard this value and you use this as new value to update your results. So it is good for dynamic performances. Okay, so online tracking of variations is possible with Kalman filter, and it is robust against measurement noise, but again convergence is poor and often suffers from filter divergence. And there are some other typical challenges of Kalman filters which are inherited in these techniques, but there are many versions of these techniques. What I'm talking about DFT, there are hundreds of DFT methods which are there, means 100 varieties of methods. There are thousands of papers on each of these techniques in literature. For example, in Kalman filter, you have unscented Kalman filter. You have then so many kinds of filters are there. Kalman filters are there, which overcomes some of the drawbacks. But again, every coin has two sides. They have some other drawbacks. So this is I'm focusing on basic fundamental techniques, but I'm not going into details of their variants in each of these techniques. So this is how, according to Fourier series, we model a signal, and then based on this, we try to find out this Hn and omega n represents your noise, and if it is modeled precisely, then you can recursively estimate Hn based on your instantaneously measured values like this. So you will have a state equation first, and then you will have update equations. So that's how you can find out the Yn from the measured quantities, right? This, right? Then nowadays there is any discussion, any lecture is it misses something if we do not talk about any artificial intelligence techniques. So in power quality also, the neural network and some other artificial intelligence techniques, they find very wide applications. You will find large number of papers and different versions of neural networks, maybe AWNN, ANN, RBFNN, and maybe recursive neural network in power quality estimations. The advantage is they are means once you have sufficient training data, and if they are properly trained, then they are very robust against noise. They are adaptive in nature with your signal, but getting proper number of training data is not sufficient, and if there is any new pattern is detected, then sometimes it's not possible to overcome, or to, if the training data is insufficient to model the complete uncertainties, then it might result into the erroneous results. So this is how it is formulated. So it is a black hole mapping. So we have some input data and some output data, known output data. Through this, we perform a training and set these parameters. And once we have set this, then for new values of xn, it will provide you A and T, means amplitude or phase or frequency, whatever you want, it can provide you. So we use a series of time samples for these purposes. Then we have a split method, estimation of signal parameters via rotational invariance technique. This is the full form of this split technique. It is like a Prony method. It is also can identify damped components and damping factor. It is also a parametric method. It is also having a high resolution without leakage effects, but again, high computational burden and model order selection is difficult in this case. Now, this was a brief discussion about different methods. Now, how we apply these methods for different power quality events. So we'll discuss one by one. Let us say first we talk about frequency deviation, one of the power quality issue, that is frequency deviation. So this might originate from generation load imbalance or system disturbances. We use zero crossing counting. Again, it involves signal processing, either Fourier transform. Again, it involves signal processing or PLL or parametric technique to find out what is the frequency of any signal. So that's how we can find out. For example, this is your frequency and it has changed here. So we can use any of these techniques to find out what is your frequency at present. So no doubt we need any of these zero crossing signal processing techniques. This is zero crossing counting. This is recommended by IEC. That's why I have discussed it. This is very simple technique, but it has its own pros and cons, but it is used in many measuring instruments in practical applications. Then voltage unbalance. For that, usually the IEC method is used. It is a specific method which defines measurement of unbalance in this way, where Q is defined by AB, BC, and CF phase voltages like this. We use DQ transform or symmetry component analysis for these purposes. And for doing any of this, we again need signal processing methods. Which signal processing methods? The one that we have discussed earlier. So I'm not going into details again for these things. Voltage sacks valve. It originates from the starting of induction motors, maybe transformer energization, short circuit or earth faults might lead into sag and swell. And the measurement methods are the IEC methods, and negative sequence components can be used for detecting these things. Basically, the IEC standard can be referred for the detailed description, because I am focusing on harmonic estimation because it covers the broad aspects of signal processing applications. So it was not possible, so I have skipped the specific details about these methods in today's talk. About flicker also, this is how we can represent the signal, and this is how the block diagram representation of a signal processing techniques that we have. We have input voltage adapter, then RMS meter. It is optional if we want to show that those values. Demodulator, weighing filters, smoothing, and statistical evaluation of flicker lever. That's how we compare it with this. I think that I have not considered. Slide is missing. PST level. Okay, might be there in the next coming slide somewhere. So basically, the flicker is defined. The unit is PST. Okay, PST, 1 PST. How much is your variation? It is defined in PST. So for that, we use this signal processing techniques in this way. Again, demodulator, you need signal processing concept, filters. So everywhere we have discussed about these things in our previous session. So I am skipping these things, right? Now let's come to the signal processing of power quality. Applications of neural networks in harmonic estimation, I am discussing in a little bit detail how we achieve it. This is about AWNN, Adaptive Wavelet Neural Network. AWNN stands here for Adaptive Wavelet Neural Network. So here, this is the architecture that can be followed. We have input layer, wavelet layer, output layer. If this is your input signal, so we can provide these sampled signals input as an input. And based on these input signals, it will provide you what is your fundamental component, what is the amplitude of first component. It is represented like this. So for training purpose, this is the problem formulation. Signal is modeled like this, and the functioning is like that. Amplitude can be detected for from different set of input time domain inputs. So it will provide you direct amplitude for different harmonics. For example, first harmonic, kth harmonic, it can provide you, right? So you need to train it first. So then training will provide you input output mapping, and then for consequently you can find it out. Parameters training of AWNN, how it has been done. It is simple representation. This is the error objective function that had been considered for termination of the training, and this is the parameter update function, and these are the update rules for different weights. For example, these are weights between middle layer to output layer, and this is the between input layer to output layer. Now AWNN is a specific kind of network which provides dual networking, means hidden layer is connected to the output, and output is also connected to input directly. So it provides you both linear and non-linear mapping together. So that's how we can complete it. There are some of the results from our research that we have done long ago. First, on simulated signals, we have demonstrated if this is our frequency components, then these are the amplitude that we have considered. So this is the relative error that we have obtained. How accurate it has been able to operate with FFT if for phase 1 means when your frequency is small. But with AWNN, if there is a frequency variation, then you see with FFT, your results are means total root mean square error is very high, where it is very insignificant with AWNN. So its performance is consistent. That's what I would like to say. With frequency changes, when frequency has been deviated from its nominal frequency, the performance of the Fourier transform, which was exceptionally well in ideal conditions, it has deteriorated to this much in practical situations or practical scenarios. And that's why this is considered to be a better option. This is a performance evaluation with some real life signals where current that was fed to the signal processor or UPS system has been recorded, and that was analyzed using this, and these are the actual results obtained from harmonics. Now there may be other harmonics also in the system, but because this is the drawback of the neural network that it can provide you only limited number of harmonics, so it has provided you this much number of harmonics. So this is the error in estimation. These harmonics were computed first, third, fifth, seventh, ninth, and 11th, and this is the error in this. Again, you see the performance is comparable to FFT, but the advantage is it requires one complete cycle, and it is providing you output with just half cycle data. Just half cycle data, not one complete cycle, but with just half cycle data, you are getting this outputs. Okay. The next method that I have demonstrated here is about split. I will skip these results, but that because these you can find in one of our research papers, which is available online. So these are just demonstration of the results of those methods, how we have done the experiments. CFL, the nonlinear loads, they have been considered. We have acquired the data using data acquisition system and then analyze the data. And these are the original signals, and these are the reconstructed signal from the obtained parameters. And this is the residual error, which is insignificant. So it is almost same. It means we have been able to accurately find out the harmonics. Now, the current scenario is about wide area monitoring of systems. So wide area monitoring means not localized monitoring, but centralized monitoring, where we are monitoring about the power quality data. So this is another aspect that is there in the field, in the scenario. I am again skipping this concept because we are running out of time. Finally, I will discuss about the hardware systems for signal processing. What are the available options? Either go for analog processing or digital processing. Now, analog processing, as I discussed in the previous session, last concluding slide, that they are designed using filter, using active and passive components like resistors, inductors, and amplifiers, oscillators. And they have drawback like with these changes in these components, the performance of these processors may deviate. Or if there is some deviation in the operating conditions, then you need to change these systems altogether. But in digital systems, you need to just retune it. But still, for high frequency and high speed applications, these are still preferred. Analog signals are preferred. Digital signals, implementing signal processing algorithms on computing processors. For example, DSP, your computers, all these things. They have many advantages such as flexibility, ease in implementation. It reduces noise susceptibility, chip count, development time, cost, and power consumption. And what are the available options for digital signal processing? Either you use general purpose processors like Intel Pentium processors, what we use in our computer systems, or you use application specific integrated circuits. We call it ASICs. Okay, or you use digital signal processors. Now digital signal processors are again, they are processors, or they are just like the microprocessors or controllers, but they are designed specifically for performing the digital signal processing tasks. So they are different than general purpose processors. How to decide whether to use ASIC or GPP or DSP? We'll discuss about briefly. ASICs are semiconductor designed for dedicated functions. So when you have to have manufacturing something for large scale, then it is good because the silicon area is smaller, lower power consumption, improved reliability, and reduction in noise system, because they are specifically designed. It means designing your chips and everything specifically for that particular processes. But it has high investment cost and less flexibility. Long time from design to market. So if you want to do some research purposes, they are not good for you. But for large scale developments, they are good. These are the typical signal processing algorithms that we need to implement. FIR filters, convolution, DFT, DCT. For these implementations, they involve lot of additions and multiplications, right? For example, hardware, it will do this multiplication in this one cycle. But if you are using general purpose processors or MATLAB or any other computing languages like C, then it will compute multiplications in different cycles. So it will involve 5 cycles to compute this. It means your time is more, computational resources will be more. So we use DSP processors when we require cost saving, smaller size, lower power consumption, or processing of many high frequency signals in real time. But GPP is used when there is a need of large memory or advanced operating systems, because these DSPs cannot work with advanced processing systems like Windows or Linux like this. But in MATLAB or other applications, then we need to use GPP. But for dedicated applications, for example, you are processing, developing some system for some controlling or developing some power quality, voltage sag or harmonic estimation, then you can use dedicated DSP processor for implementing that Fourier transform or something. These algorithms are pre-built in these DSP processors and they are easy to implement. Now, when you are choosing, you have to choose between floating and fixed point processors. Depending upon the applications, you can choose it. Now, there are different, especially from Texas Instruments and some other manufacturers, we get a different series of processors, DSPs, digital signal processors. You have to choose depending upon your applications, whether you need an availability of budget, what you have to use. If you need some wireless applications also, internet audio players, then you should choose this series of processors from the Texas. If you want high-end performance, ease of use, then use this series of processors. They provide all kind of applications, multi-channel and multi-function apps. But in 2000 series, you can use it for motor control, storage, and digital control systems, but they have very limited applications and limited applicability. So this is how you can use hardware systems. So finally, to conclude, the processing of power quality variations is well defined in standard documents, and well understood signal processing tools are sufficient for most applications. But for specific applications, like where you have time variations, non-stationary signals, then we need specific applications of signal processing tools. There are, however, 2 areas where we need further development of signal processing tools, that is fast voltage fluctuations and high frequency variations. These are still open areas where we need to focus. An important application of signal processing tools is the location of sources of power quality variations. This is right now in practice. From the measured, we try to find out, for example, in a grid, multiple users are connected at a point of common coupling. So based on this common measurement, just to find out who is the culprit, who is polluting our grid. That is the another area of application of signal processing that is one of the important application that is prevailing right now and that you can pursue. So this is about the signal processing application. Thank you very much. Now, because time is running, I invite very quick questions from you if you have any. And in fact, your feedback also about the talk. If something we need to include, yes.
Thank you, sir. Now the podium is open to participants for questions. Actually, I am Dr. Bikram Das, one of the coordinator of the same FDP.
Okay, okay.
So Jain sir is now out of this meeting, so I'll handle the rest part. So participants or any questions?
Sagar is asking that FFT is less accurate than DFT. I have told you that FFT is a mechanism to implement DFT in digital form. So you cannot say that one is FFT has different versions. For example, you can use Radix 4, Radix 2 in different mechanisms. So it is a fast way of implementing DFT. You can use other mechanisms also, right? Is that clear?
Yes, sir.
Sir, I am having one question.
Yes, please.
That, sir, you have told about non-parametric methods are like wavelet transform in, in Hilbert transform. Sir, if in wavelet packet or wavelet transform, we decompose the signal and we get some coefficients like detailed coefficients and approximate coefficients. Sir, in just like that, in Hilbert, we also get like intrinsic mode function and all these things. So what is the basic difference between wavelet and Hilbert?
Okay. You see, in wavelets, in Fourier transform, we have defined a sine wave that is indefinite, means from minus infinity to plus infinity. So we don't get any time information, right? So for that, we came up with wavelet transform, where wavelets are a small time duration. Now, still they are fixed. Wavelets, once we have used, so mother wavelet we have defined, so that is fixed for particular application. Whereas in intrinsic mode function, we have further flexibility. So it is next stage of flexibility that we have obtained in HST using intrinsic mode functions. So basically we use empirical mode decomposition, EMD and IMF. So that is the concepts which we use in HST.
And sir, another question from my side. Sir, you have shown some of your practical hardware validation where you have used some data acquisition units and all these things. Sir, I'm having the question because I'm also working on such power quality monitoring and detection principle. So, and for the in the initial stage, we are developing some mathematical modeling of synthetic signal, and then when you take this research into some update level, we have to get the real-time signal.
I think it will be better for such cases if you contact me personally. You can take email address from Dr. Jain. So it is SK Jain. In fact, I can type it here itself. So if you have any queries, any one of you, even after this, you can anytime you can write me a mail. So in a text box, I have provided my email address, so you can contact me. We'll try to discuss about this one.
Okay,
because that will take a lot of time, means to demonstrate about the hardware signals, how you have to acquire these things, right?
Sir, if it is a limited resource, if you only have some real-time simulators like OpenRT and all these things, so can you validate the MATLAB models in directly without using the practical real-time signals?
Not your not clear, means your voice is also breaking. Your question is not clear to me.
So my question is that if we have limited resources, like we are not having some data acquisition tools, so if we directly make the mathematical modeling like synthetic signal in MATLAB platform, then we can we are having some digital simulators like ATAL-FDP. Then can we make the use of it to validate in terms of real-time signal?
Okay, in ATAL-FDP and any real-time simulators, you have a provision of measurement of those signals that you are generating here. So this hardware in loop kind of concepts is there. Okay. So in those cases, you can acquire those signals, but at least you need those signals from somewhere. So that is quite possible. In fact, I have used ATAL-FDP signals in one of my research articles I have discussed here. Right?
Okay, sir. Okay, sir. I'll definitely go through it.
Okay. So any other questions from?
Regarding noise, you have told like 20 dB noise is larger than 40 dB noise, and
Just a minute,
robust.
Please. Okay, please.
Yes, sir. Generally, for training a well system, like how much dB noise should be working accurately?
Vikramji, are you getting his voice clearly? Because I am not getting.
His sound is breaking. His sound is not clear. His sound is breaking.
Srikar, your sound is breaking.
Are you there, Srikar? Okay, anybody else? Any questions?
I think Vikramji, they can on my email address, they can drop me a mail. What are their queries? So I will just answer their queries. Okay.
So you'll like to wind up here. If you have any more queries, you can please kindly contact sir. The mail ID is already provided in the chat box. skjain@IIITDM.ac.in. Otherwise, you can get it from the Jain sir also. So,
sir, can you provide us your PPT?
Yeah, I will try to provide you. No issues.
Yes, I will definitely provide the PPT because the documentation is also required. Maybe not be the full. A portion of it may be provided.
Yes, I'll provide you. I will mail it to the organizers and they will provide it to you.
Yeah, sure. So we'll wind up now. Thank you, sir. Thank you.
Okay, thank you very much for your patience hearing, everyone. Thank you very much. Goodbye.
Thank you very much, sir.
Thank you, sir.
Shall I leave now?